So the rate of a chemical reaction is measure how fast the reaction either makes products or uses reactants. Those things both happen at the same time, right? Here we have a visual illustration of a reaction with a fast rate and a reaction with a slow rate over the course of time. So both of them, we're starting with just the little reactant molecules at the beginning. There's no product present. And here is maybe 15 minutes, or let's say seconds. 15 seconds, 30 seconds, 45 seconds, right? Time is going on. So this fast reaction we see within that time period, all of the reactants completely react, and all we've got left at the end is the product. The slow reaction happens much slower, and so we're forming product as we go along, but when we get to the end of the time, it's not done yet. We have some product, but there's a bunch of reactant that hasn't reacted yet. So chemical reactions happen at different rates, and the rate is how fast they either make product or use up the reactants. Any questions yet? Questions are wonderful, and I want you to interrupt me when you have questions. So rate is how much a quantity changes in a given period of time. A rate that we're more familiar with is speed, right? So how fast is your car going? What is the rate of travel of your car? Well, it's the change in a quantity, here a distance. Your location changes by what distance? Distance traveled in a given period of time. How long did it take you to travel that far? So speed is change in distance over change in time, which we could represent as delta x over delta t. And hopefully you remember from Chem 1A that delta means change in. And so when we say delta T, what we mean is the final temperature minus the initial temperature. If we did initial minus final, we'd have the same number, but the sign would be different, and a lot of times the sign is important. It's always final minus initial. So for a chemical reaction, instead of distance traveled, we're looking at changes in the amounts of either the reactants or the products over the course of time. Any questions? So let's look at an example. This is a reaction that occurs in the gas phase. All the reactants and products are gases. Hydrogen gas reacting with iodine gas to form hi. Isn't that what that says? It's all caps. It's yelling. Hi! Hydrogen iodide. That's like my second favorite molecule. My first one is no. Nitrogen monoxide, NO. Right? Yelling. I have 6 kids. I say that a lot. Okay, so there's high. So if we look at the change in concentration of the reactants start at some number and their concentration goes down as the reaction occurs, right? Because they are reacting and they're not going to be there anymore. So the change in concentration of reactants is going to be negative because the final concentration is always lower than the starting concentration. Well, a reaction rate is positive because we decided that we're always going to report it as a positive number. Now, if you're traveling up and down Highway 99, you don't say, well, I was going minus 75 miles an hour. What does minus mean? You were going backwards? Yeah, we just don't talk about that. Speed doesn't have a direction associated with it, right? And so just like that, a reaction rate has to be positive. So if we're looking at the change in the reactant concentration, we have to do something to make this a positive quantity. So the rate of the chemical reaction is the change in concentration of hydrogen over the change in time. But because this is a negative number, we're going to multiply it by -1 to make it a positive number. Now, why didn't they just use absolute value? There's maybe some reason, but they didn't, and we have no say in that, so we just need to do it. So this then represents the hydrogen concentration at time 2 minus the hydrogen concentration at time 1 divided by time 2 minus time 1. The difference in concentration divided by the difference in time. When we look at this equation here, it's like, wow, things are getting a little, that kind of looks like calculus or something. No, if you've had calculus, there are some things in here where you'll understand, oh, yeah, calculus is how they did that. But you do not need to know any calculus in this class, okay? I myself mostly forgot all of it as soon as I was done, a long, long time ago. So we can express the rate as the change in the hydrogen concentration, or we can express the rate in terms of the change of the iodine concentration, the other reactant, right? So again, the change in that concentration, it's going to go down, it's going to be a negative number, divided by the change in time, which is always a positive number, times -1, and we're going to get a positive number. Any questions? We can also define the rate with respect to the product of the reaction. So here, the product is high, right, 2HI. Well, product concentrations increase when the reaction occurs, and so the change in concentration is always going to be positive. So we don't need the negative sign. So we need a negative sign when we're talking about changes in reactant concentrations. We do not need it for product concentrations. So here the rate equals, and they put this plus sign in here, not because you need the plus sign, but just to kind of make it stand out, this is not a negative sign like the other one was. And here we have delta HI over delta T, which reminds me, so what do those brackets mean? Concentration. So that means the concentration of HI. And that is almost always measured in molarity, moles per liter. So this doesn't have a unit specified because we understand that it's molarity, moles per liter. So the change in the concentration of high divided by the change in time. And then we've got this 1/2 in front. What's that doing? Well, we need this in here because of the stoichiometry of the reaction. When we use up 1H2, we make 2 highs, right? So this is getting formed twice as fast as the hydrogen is getting used up. But the rate of the reaction has a single value. So we're going to multiply by 1/2. Yeah, I kind of just said this. So the concentration of HI increases at twice the rate. So in order to get a single rate for the entire reaction, we have to multiply by 1/2. So this is coming from the coefficient. And we'll see in a minute that we don't really have to think too much about where to put the 2. There's a pattern. Any questions? Good question. Is it always half, or is it because this is a 2? It's because this is a 2. If this was a 3, it would be 1/3.
So always 1/.
1/. Whatever the coefficient is, it's 1/. The coefficient. Now back here, why don't we have 1/1 here? Well, this has there's no coefficient written, is there? But what is it? We understand that it's 1. Well, what's 1/1? It's 1. And if you multiply something by 1, does it change anything? No, it doesn't. So chemists a lot of times just leave 1s out of everything, right? So here we have an unwritten 1, and what you can't see here is an unwritten 1/1. Okay? So it's always 1/. The coefficient. We'll be using a lot of graphs in this course. Here's our first one. So this is a graph of the concentration in molarity as a function of time in seconds. And so here, color is that? Is that green? I think it's green. This line, the green line, is the concentration of hydrogen. So at the beginning of the reaction, we had, it looks like if at 0, we probably had about 1 molar hydrogen. As the reaction goes on, the hydrogen is getting consumed, and so the hydrogen concentration decreases and decreases and decreases. But it's not a straight line, is it? It's a curve. There are situations where it's a straight line, but mostly it's a curve, and we're going to learn about that another day. The red line is looking at the concentration of the product. Well, the product starts at 0, and as the reaction occurs, product is being made, and so the concentration is increasing, right? So reactant concentration going down, product concentration going up. The HI is increasing twice as fast as the H2 is decreasing because of the stoichiometry. For every one of these that gets used up, I get 2 of those. Any questions? The rate is not shown directly on the graph. The rate is equal to the slope of this line. It's the change in concentration divided by the change in time, right? So we said that the rate is equal to, for reactants, it's negative the change in the reactant concentration divided by the change in time. Well, this is a curve, so the slope is constantly changing, but at a given point, we could draw a tangent to the line and find the slope of that. So here's a tangent line, and then we're looking at the difference in the rise, which is the change in concentration, divided by the run, which is the change in time. So this rate is equal to negative, the change in H2 is minus 2.8 moles per liter. The change in time is 40 seconds. So the change here divided by the change there. Then you should always bring your calculator to class, and you should pull it out and do these calculations with me. Because sometimes things go badly with calculators. So the rate I get is 0.007. That would be molarity per second. So do the calculation along with me, because I make mistakes sometimes and I need you to tell me when I did it wrong. Okay? If you try it several times and you're just not getting the right number, feel free to say, hey, it's not your fault. You're not having trouble with your calculator. My calculator is misbehaving, and I'll come over and be stern with it and tell it to shape up and show you what you're doing wrong. Because we have to understand how to communicate with our calculators to get the right answers. So if we wanted to look at the rate in terms of the concentration of HI, we could draw a tangent line on that curve. This is going to be at the same time that looks like they're doing this at 50 seconds. So the rate here is also going to be the change. So the rate is equal to, now this is a product, and so it's positive, and because of this coefficient of 2, we need to have 1 over 2, and then we're looking at the, whoops, I forgot the delta. Delta HI divided by delta T. So that's 1/2, and here the change in concentration was positive, 0.56 moles per liter, and the change in time, again, is 40 seconds. And that one comes out to be 0.014. No, sorry. Comes out to be the same. Molarity per second. I forgot the 1/2. So whether you calculate it from the reactant or the product, we're going to get the same reaction rate answer. If we look at just the change in HI over time, it kind of went off in a direction I didn't anticipate. It's okay. Rate of HI increasing. I did it better yesterday. That's going to be the change in concentration over the change in time, which is 0.014 molarity per second. So the rate of change of this concentration is twice as big as this one. And that's why we put the 1/2 in here, because the balanced chemical equation, stoichiometry, tells us that that's occurring twice as fast. And so we have to divide by the coefficient. Questions? That was kind of murky.
Should we do this, like, do that graph and do the tangent and do these calculations and this stuff? Or just the rate?
So we're going to talk about this, but as we'll learn in just a minute, this is what's called an instantaneous rate. And the rate changes as time changes. And so knowing the instantaneous rate is actually not very useful. So this is more conceptual about how these would be calculated. We're not actually going to be drawing tangent lines. There might be a couple of homework assignments where you have to draw 1 or 2, but that's it. Good question. So if we went through and looked at average rates of reaction, see, did I miss something? No, I didn't. Okay. So if we look at different time points, so here's every 10 seconds, and we're looking at the concentration of H2. It's going down, right? In order to do the actual instantaneous rates, we would have to draw tangent lines all over the place, and nobody wants to do that. We can also look at what's called the average rate. So in this time period, 0 to 10 seconds, we can say, well, what's the change in H2? And divide by the change in time. And so that's negative 1.81 divided by 10, and we get this as our reaction rate. And so we can do that for each time period. So this is for this time period from 0 to 10. This one down here is the rate from 90 seconds to 100 seconds. And what we see is that the rate is going down. Does that make sense? It's getting slower and slower and slower. And one of the things we'll be talking about is, why does that happen? So the instantaneous rate is the rate at any one point in time. And that's what we get by drawing the tangent line and calculating the slope of the tangent line. Okay? It's actually not all that useful, but that's how we would do it. I think this is where I was supposed to do the calculation. I did it early, sorry. Okay, so we can have a general equation, a general definition of reaction rate. So here's a generic equation. And this is lowercase a represents the coefficients, and the capital represents the chemical formula. So A moles of A reacts with B moles of B to form C moles of C and D moles of D. We can write an equation to represent the rate from any one of these 4 things. So in terms of change in A reactant, we need a negative sign here. It's the change in concentration divided by the change in time, and we multiply by 1 over the coefficient, 1 over A. So the first ones we didn't have a fraction there because the coefficient was 1, and 1 over 1 is 1, and we don't need to write it. Okay. Here for the other reactant, again, negative, change in concentration of B over change in time, and we have 1 over B, the coefficient, to give us the rate of the reaction as a whole. For products, done the same way, except these are positive numbers. Again, 1 over the coefficient times the change in concentration over the change in time. So if we know the rate of change for one of these things, we can calculate the rate of the reaction. We can also calculate the rate of change of anything else, but it's only good at one point in time. It doesn't allow us to predict, well, what's going to happen in 100 seconds? You can't predict that just from this instantaneous rate. Okay, so here's our first example. Consider this balanced chemical equation. We've got 3 reactants here and 2 products being formed. In the first 10 seconds of the reaction, the concentration of I minus dropped from 1 molar to 0.868 molar. Cool. Calculate the average rate of this reaction in this time interval. So, what's the time interval? The first 10 seconds. Well, it started at 0 and ended at 10, right? So delta T is going to be 10. So we'll write our equation here. The rate is equal to, I minus is a reactant, so we need to have a negative sign here. And then for the fraction, we're going to use 1 over the coefficient. The coefficient here is 3. So this is 1 over 3 times the change in concentration of I minus divided by the change in time. And this here is telling us what the change in time is. So this is the same as the final concentration of I minus minus the initial concentration of I minus divided by the change in time. They didn't just tell us what delta I minus is, but they gave us the numbers, right? So 1 over 3, and then the final concentration is 0.868. And the initial concentration was 1 molar. And we're going to divide by delta T, which they just told us was 10 seconds. So do this on your calculator. So then we do the animation on the slide, and it shows the correct answer up here. I do this in 1B because these calculations I make more mistakes in. And it's really, really frustrating when I do a whole lecture and do this great example, and I made one stupid little mistake, and nobody said anything. And I posted on YouTube, and 3 years later, some guy from England says, "Are you stupid? Don't you know that 3 minus 1 is 2? Yeah, so if I do it wrong, please stop me, okay? I'd like to say I make mistakes on purpose, just to see if you're paying attention. But it's not true. I just make mistakes. Any questions on how we did that problem? So there's a part B. Determine the rate of change in the concentration of H plus during this time interval. And what they're saying here is, well, the rate of change in concentration of this is delta H plus over delta T. Well, hopefully that sounds a little familiar now. We can do the rate of reaction in terms of the change in H plus concentration. Well, H plus is a reactant, so what do we need at the front? A negative sign. And then our fraction is going to be 1 over what? 1 over 2, because of the coefficient. So it's 1 over whatever the coefficient is. And then we've got the change in H plus concentration divided by the change in time. So that was the equation we learned how to write. What are we trying to find? We're trying to find delta H plus over delta T. Right? This is what we're trying to find. Well, in our equation, that is this whole messy thing right there. So we could call that X, right? We could say, well, the rate is equal to negative 1/2 times X, the thing we're trying to find. That might make it easier for you to understand how to do the rearranging part. Well, we know what the rate of the reaction is. We just calculated it in the previous problem, right? It was 0.0044 molarity per second. So visually, it's really messy here, kind of hard to get your brain around that you're solving for this whole thing. And so that's why I put an X in there, because that's a little easier to see. So if I give you this equation down here, everybody's okay with, oh, well, I multiply by 2 and divide by negative 1, and X equals negative 0.0088. But if we're looking at this guy up here, our brains just kind of check out. We're like, there's 2 letters there. I can't do that. But we want the whole thing, okay? So that is equal to the change in concentration of H plus over the change in time. It's negative. Is that okay? It is okay because this is a reactant. So its change is negative. It's going down over time. Any questions? There's a part C. Okay, there I got the correct answer. Part C, predict the rate of change in concentration of H2O2 and I3 minus during this time interval. So this is very similar to part B. They're asking us to find the change in concentration of the third reactant and also of one of the products. We're going to do the same thing. So the rate for that first one is a reactant. So we need a negative sign. And what would the fraction be here? What's the coefficient? It's 1. So this would be 1 over 1. And for some of you, just mentally, it's more satisfying to have always the fraction there. 1 over the coefficient. The coefficient's 1. I'm going to write 1 over 1. Great. No harm done. And then the change in the H2O2 concentration over the change in time. Right? That's kind of the first thing we learned today, how to write those equations. Well, so what we want to find is that whole mess, which is this box right here. And we know what the rate of the reaction is, so we can put that in. So I'm going to do this without putting the x in there. But feel free to do it on your paper if you want. What do I have to do to solve for this? I just need to change the sign, right? Multiply both sides by -1 or divide, whatever makes you happy, right? If negative of that quantity is 0.0044, then positive of that is, the opposite in sign is -0.0044. So the rate of change of the H2O2 is the same as the rate of the reaction. That's going to happen whenever the coefficient is 1. So let's do the next one. So here we want the rate of, we've got the rate, and that is equal to, this is a product, right? So it's going to be positive, and the coefficient is 1, right? So, to be really thorough, you can write plus 1 over 1. All of that is unnecessary. Delta I3 minus over delta T. And again, this is the thing that we're solving for. And that is equal to 0.0044 molarity per second, because that's the rate of the reaction that we calculated. So what does the thing in the box equal? It's just this, right? So the change in I3 minus divided by the change in time is also equal to 0.0044 molarity per second. Any questions? Oh, good, I got the answers right again. So this is what the book calls a conceptual connection, meaning we shouldn't need a calculator for this. So for the reaction, A plus 2B goes to C under a given set of circumstances, conditions. The initial rate is 0.1 molarity per second. What is the change in concentration for B under the same conditions? So this is the reaction rate, and we're asked for the rate of change for B. Well, it's multiple choice, so one thing you can do is just eliminate any answers that you know are wrong. The rate of change for a reactant is going to be positive or negative. Has to be negative, right? So D cannot be the answer because that's a positive number. So now we've narrowed it down a little bit. We do have this coefficient of 2 here, which is kind of complicating things, right? If it was A, we'd just say, oh, well, it's the same as the reaction rate. We just have to make it negative and we're done. Well, now that we said that to ourselves out loud, we're like, oh, well, that would be the rate of change for A, would be this one, so it can't be that one. So what we've got left is we multiply by 2 or we divide by 2. And this is where you can kind of go in circles in your head. And you can do this just by thinking it through. I find that I do it wrong that way a lot. So what I would do is I'm just going to write the equation for it to help myself. So the rate of the reaction is equal to negative. The coefficient is 2, so we have 1 over 2 times the change in concentration of B divided by the change in time. And that's the rate of reaction in terms of B. The rate equals minus 1/2 times this. Well, again, like in those previous problems, this is the thing we're trying to find. So, I've got the rate, am I going to multiply by 2 or divide by 2? I'm going to multiply by 2. And so, this must be the answer then. It's easy to think, oh, well, it's 1/2 times that. Yeah, but this is what I'm trying to find, not the rate. I know what the rate is. I'm trying to find this thing, so I have to move that to the other side. So did we get it right? Yes, we did. Okay, we're done with the math part. So how do you measure a reaction rate? Well, you need to be able to measure the concentration of one of the species, one of the reactants or one of the products, over the course of time. And there's the train again. It's not nearly as loud as it is in 240. 250. 240, yeah. 240 is really bad. It'd be better if I had the door closed, but it's stuffy in here, so I'm not doing that. Okay, so there's 2 ways we can approach the problem. One way is to continuously monitor the concentration. And that would be really appropriate for a fast reaction, maybe something that's going to be completed in less than an hour. We're going to have something set up so that we can monitor the concentration constantly. But if we have a reaction that happens over a very long time, you could have a reaction that takes 2 weeks to complete, right? Or 12 hours or something. We don't want to be measuring that whole time, so then we may just sample at various times. Say the reaction takes 6 hours. Well, maybe we'll sample every 15 minutes or something. We'll find out what the concentration is. Well, how do we measure the concentration? These are techniques that can be used for continuous monitoring. One of them is polarimetry. Some chemicals will change the degree of rotation of plane polarized light, and that change is going to depend on the concentration. So this is probably something you've never heard about before. It's okay. It's not going to be a deal in this class, but when you go on to OChem, they'll talk about polarization of light and how chiral molecules can change how the light is. It's very interesting. But that is a technique that can be used. It only works for certain compounds. Another thing you could do is you could measure the total pressure. So if you have a gas mixture, the total pressure of the gas is stoichiometrically related to the partial pressures of the individual components. So if you have this reaction 2N2O is making 2N2 and O2, we have 3 moles of gas in the products and 2 moles of gas in the reactants. So we expect that as time goes on, the pressure in the container is going to increase. We monitor that pressure and we can figure out what the concentration is. Spectroscopy is another thing we could do. This involves passing light through a solution and seeing how much light is absorbed. We have an illustration of this. So this is an illustration of a spectrometer. So we have some light source, and then we block out a lot of that and just let light through a slit. And that goes into, this is called the monochromator. It involves a prism, which separates that light into different wavelengths. And then we can select the wavelength that we want by moving a slit here. And so we could select red light or blue light. Here they're selecting this kind of bluish green light. And so that light passes through the sample, and the amount of light that passes through is monitored by a detector hooked up to a computer. So the higher the concentration of the one component in here, the less light comes through. So this is a type of reaction that you could use that for. H2 plus I2 making, again, our friend high. The I2 gas is violet in color. It's really pretty. It's purple, right? And so the more intensely purple it is, the less light will come through, and so that amount of light coming through is related to the concentration, and that's a way that we can measure the concentration. We will be using a spectrometer in one of our labs. Any questions?
I did not get how to do like the total pressure.
The total pressure? So the point here is really just to kind of give you an overview. We're not really expecting you to do anything with this information right now. So this is just an example. As this reaction occurs, and this is something that's a little hard to get your mind around from Chem 1A, the reaction just doesn't go. It's not like, okay, well, we started with this and now all of a sudden it's all split up. It takes time. And as this occurs, the pressure in the container will increase because we're going from 2 moles of gas to 3 moles of gas. And so the increase in pressure tells us how much of the reactants, well, how far the reaction has gone.
How can identify from the pressure the concentration?
Well, that involves some math that we probably don't want to talk about right now.
Okay.
Yeah. Yeah. Any other questions?
So the technique for continuous monitoring, they are for identifying the concentration, right?
Yeah, for looking at the concentration, and there are other techniques. These are just 3 that we're talking about. Not all techniques can be used for continuous monitoring
Which is the concentration.
of the concentration.
Oh,
Yeah.
okay.
So for periodic sampling, for that slower reaction, where maybe we're going to sample it every 15 minutes or something, what we're going to do is we're going to take a sample from the reaction mixture and measure the concentration in that sample. When we take a sample out of something, we call it an aliquot. Aliquot is just, we took a sample. So we take out the sample and we measure it. And so then there are different techniques that can be used for measuring the amount here. Common techniques are titration, gravimetric analysis, and gas chromatography. So titration, you did titration in Chem 1A, right? So say one of the reactants or products is an acid. Well, we can take a little sample of a reaction mixture and titrate it and find out how much of the acid was in that volume. Like say we took a milliliter and we titrated it and we found out that there was, X moles in there. Well, then we divide by the volume and now we have the concentration that was in the sample. That can't be done continuously though, right? Or with a fast reaction, because as you're pulling it out and beginning to titrate it, in that little sample, the reaction is still going on. It's still progressing. And so these sorts of things can only be done with slower reactions. So titration, gravimetric analysis would be maybe there's something that you can precipitate into a solid, and then wash everything else away, and weigh it. So gravimetric, measuring by gravity, measuring how much it weighs. So that's another technique. A third common technique is gas chromatography. And this can be used to measure concentrations of more than one component in a mixture. And this is just kind of an overview of gas chromatography. You have some carrier gas. It's usually something that's very unreactive, like nitrogen or helium. And so you have gas that's running through an injection port, and it's flowing through this column. This column is a tube. It's very, very tiny, and it's very long. And so the gas is going through kind of like a straw and coming out through a detector, and the computer is hooked up. And so if something that the detector can detect comes through, we'll see a signal. When it's just the carrier gas, you just see it down here. When something else comes through, it goes up. So we take our aliquot and we inject it here, and as the sample goes through the column, the inside of the column, of course, has to be made of something, right? Might be silicate or lots of other things, plastic or metal or whatever. They can put coatings on the inside. Well, the different components in that mixture are going to be attracted to the inside of the column in different ways. Some of the things might be very attracted, some of them might be not attracted at all. So as the components go through, some of them slow down because they're like kind of sticking to the walls. And some of them don't slow down and just keep going right through. So the components of the mixture are going to come through the detector at different times. And so here we see something came out here, and then the signal went back down because that one was pretty much all gone, and then something else was coming out. And so this allows us to separate components and measure their concentrations. Yeah, that's about all I have to say about that. Any questions? And again, talking about these techniques is just to kind of give you a hint, a picture of what sorts of things are out there. You know, if you think about all of chemistry and all the research and the techniques and the different things, I don't know even a fraction of it. In graduate school, I did analytical chemistry, so I am familiar with these things. I've used a gas chromatograph before. Very cool. Do I know everything about it? Absolutely not. I know just enough to be dangerous. But there's all kinds of different techniques, and each of these techniques, you can spend your whole life studying and optimizing and making it better. But one of the fascinating things is, you know, you've got to say a reaction occurring in a solution, and it's colorless, and you know, you start with the reactants and you end up with the products, and you're standing there looking at it and you can't see anything happening. You can't tell that anything is happening, but a chemical reaction is occurring. And so how can you measure these things that we can't see? And that's what a lot of people in chemistry find fascinating, because it's a puzzle, right? And so we have all these different techniques. Some of them are just the detecting, and others are like, okay, well, this detector is great, but it detects all kinds of things, and we just want the one thing. And so then you need to separate and detect. And that's the end.